coming back to where we are in the notes, so last week we looked at the definition of the derivative. So this is the derivative is this quantity which gives you an instantaneous rate of change for a function, tells you how the function is behaving at a particular point, whether it's increasing or decreasing. This one. Okay, so we discussed the definition last time. Here, definition 4.3, which is back on page 39. And we looked at a few basic examples of simple functions and what their derivatives were. We also looked at the kind of table of results for derivatives of standard functions. This is the table appearing on page 41 and 42. That's an extract from the faculty formula handbook, which you'll have use of in examinations and so on. So we'll make use of that to look up standard derivatives and integrals. But there are also a number of important properties of the derivative that we need to know about. We want to explore and justify, see why they're true. And these are chiefly properties about how the derivative interacts with the operations that we can do amongst functions. So that once we have the table of standard derivatives of some kind of basic building block functions, then using the properties of the derivative, we'll be able to obtain derivatives of any more complicated compound functions that are built out of the kind of standard functions that we have on the table. Okay? Because all the different functions we're going to encounter, we can't find them all on the table, right? But typically, we'll encounter a complex compound function which is constructed using the operations of function addition, multiplication, division, and importantly, composition. It's constructed out of simpler functions, and we can see the derivatives of the simpler functions on the table. And so we need these various properties to tell us how to then pass to the derivatives of the more complicated functions. Okay, so that's what we're going to investigate today. So the first of these properties are on page 43. As we've done at similar points up to now in the course, when we've been looking at convergence of sequences of series, limiting values of functions, continuity, the first property we turn to is the property of linearity. Okay? So linearity here concerns the situation where we've got two functions. So here in theorem 4.5, we've got two functions, g and h. We take it that we know the derivatives of g and h, that they have derivatives. And linearity suggests we're going to take a linear combination of those two functions. Okay? So we've got two real coefficients, alpha and beta, and we're taking a linear combination, alpha times g plus beta times h. So this gives us a new, more complicated function, f, so to speak, more complicated than g and h alone, perhaps, because it's built as a mixture of g and h. And so the question is, what is the derivative of f? How does the derivative of f relate to the derivatives of g and h? Okay, so you can see the result there. It's quite nice. It says, well, in one sentence, it says that differentiation is a linear operator. So when we apply the derivative d dx to a linear combination function f, we can say that its derivative is the linear combination of the derivatives of the ingredient function, so to speak. Okay? So the derivative of f is going to be alpha times the derivative of g plus beta times the derivative of h. And what we'd like to do is to fully justify that with reference to the limit definition of the derivative that we introduced last time. Okay? So I'll just prepare the camera for capturing the screen. Now, the structure of these arguments, the way we lay them out you should very much compare them to the other proofs of linearity that we've done for convergence of sequences, series, continuity, limiting values of functions, and so on. There's very strong similarities that you can spot between all these different arguments. They're really all the same argument, just put into different contexts. Okay? So this is theorem 4.5. Okay. So, well, just to make the assumptions explicit, that's contained there in the statement, we assume that the functions g and h, that they're both differentiable at a point A. Okay. So it's going to be focused at a particular point A in the domain, and we're going to show that this linearity property holds at any point in the domain. We'll just assume that the domain, we won't place any restriction on the domain of the functions. Just take this, that this is any real number. Okay. So what does that mean? Well, it means that the following two limits exist and are given the names the derivative of g and the derivative of h. So the derivative of g is this limit. The limit as x approaches a, g of x minus g of a over x minus a. So all I've done there is written out the definition of the derivative of g. And that definition we just looked at a few moments ago. And h prime, the derivative of h evaluated at a, this is equal to the limit as x approaches a, just exactly the same thing, but this time talking about the function h. Okay. So remember, this is the limit of the relative change in value, the relative change in value of the function when evaluated at a nearby point x. So the absolute the absolute change in value, that's the numerator h of x minus h of a, the difference in values, but it's relative to the change in value of the argument. So we express it as a proportion over x minus a. So that these two limits exist. So we want to prove what the task is, what needs to be proved here, is that the appropriate limiting value of relative change in value for the function f, that exists and has the required form. Okay? So we need to demonstrate now, or we need to show why the derivative of f at a exists and why it has the required form. The required form being a linear combination of the derivatives of g and h using those same coefficients, alpha and beta. So this is a good way to structure your proof. Make very clear what the assumption is. Make it very explicit. We could have just left it at assuming g and h are differentiable, but it helps the reader reading the proof, and it helps us in constructing it to actually write out explicitly what that means, even though it's really just the same statement, once for g and once for h, but it helps to visually see it on the page, the reader, and both for us in constructing it. So let's attempt to obtain this derivative of f. So by definition, this is the limit as x approaches a of f of x minus f of a over x minus a. But the question is, at this point, I'm not sure that this limit exists yet. Okay? I can write it down on the page, the limit as x tends to a at this, but sometimes limits exist and sometimes they don't. So I haven't given the justification yet for why this exists. Well, let's work out what this is in terms of g and h, okay? Because we have the we have the construction that f is just alpha g plus beta times h. That's the f we're talking about. So this limiting value must be the limit as x tends to a of alpha g plus beta h, this function evaluated at x, minus alpha g plus beta h evaluated at a, and all of it relative to change in value that's happening with the argument. Okay. All I've done is just substitute the representation alpha g plus beta h for f in the definition of the group. I'm still not sure that this limit exists. Okay, I have to show why this exists. So even though I've just written it down, but maybe this limit won't exist. But you see, I know that the corresponding thing focused on the function g is. That's by assumption. And similarly for h. Well, I can see my g and h down here. At the moment, they're mixed up. They're tied up together. The g and the h in the definition of this single function. But I know, I'm assuming that the limit applied to g exists and the limit applied to h exists. So to see that that implies that this one exists, I just need to tease apart the g and the h down here. So that I'll see this expression emerging and see this one emerging. I suspect I'll be able to do that because I can see the g and the h down here, but I don't yet see this exact quantity here or this one. Okay, so the thing to do is to tease apart the g and the h. Well, how are we going to do that? Well, we're going to use the definition of what these operations are here. So this is a linear combination of these functions. So what is the definition of a linear combination of functions evaluated at x? Well, in chapter 3, when we examined functions and introduced the notion of an operation amongst functions, we said that, well, that was nothing but alpha times the value g of x plus beta times the value h of x. Yeah? And similarly for this here evaluated at a, this is going to be alpha times g of a minus beta times h of a. And this is all still over x minus a. Now there's lots of brackets floating around. Just be aware of the different meanings of the brackets. I mean, this alpha times g of x, so this pair of brackets is just kind of separating the g of x away from the alpha, but it's just this number alpha multiplied by this number g of x, whereas the brackets here around x, they're the brackets that go around the argument to a function. So this is the function g evaluated at the argument x. Well, okay, I've broken apart the g and the h there. That's good. Now I should just gather the g's together and gather the h's together. So, and factorize out the common factor of alpha as I go. So this is the limit, in a large bracket here, g of x minus g of a, all over x minus a. So I've obtained this by taking the alpha g of x minus alpha g of a, and that's over x minus a, and just separating it off. That's what you're allowed to do. You can take if the numerator of a fraction is a sum, you can split it up into the two fractions, add it together. And similarly, you've got beta times h of x minus h of a, and that's all over x minus a. So now this definitely looks like good progress. I've taken my expression up here, which had g and h tied up together, bound up together. I've now completely separate, well, almost completely separated. Yeah, question. G of x ties G of a. Sorry, thank you. G of a, of course, that one there. Well spotted. And they're both still within the same limiting process. But of course, what have we already proved for limiting processes of functions? We've already proved a few lectures ago, before Christmas or just after Christmas, we've already proved that the limiting process for functions is linear. And here I'm taking the limit of a linear combination of quantities. Alpha times this fraction plus beta times this fraction. So using the linearity property of the limiting process, I can say this is alpha times the limit as x approaches a of g of x minus g of a over x minus a, plus beta times similar limit involving h. There's a key justification needed here. I mean, the justifications here are just the definition of these function operations, and then just algebraic manipulation to get you to here. But here we've used by the linearity of the limiting process, which is something we've already established. And of course, so I said at the start, our task was to set out to show that this derivative of f exists and it has the required form. Well, here I see it, I've expressed it as a linear combination of these two limiting processes. But these two limiting processes are assumed to exist. These two limits are assumed to exist, okay? So if my f prime of a is alpha times something that exists plus beta times something that exists, then the f prime a exists. So this is exactly alpha times g prime of a plus beta times h prime of a. That's true by assumption to start. Those are the conditions in the theorem. Assume that g and h are differential. So from beginning to end there, I've got the required formula. The derivative of f is indeed, skip out all the intermediate stuff, we prove that the derivative of f is alpha times the derivative of g plus beta times the derivative of h. And we see how it crucially depends on the same property, this linearity property of something we've already considered, limiting values of functions, just as we considered limiting values of sequences, series. So that gives us complete confidence in this property now, that the differentiation is indeed a linear operator. Any queries about that? Or I've tried to show good practice there in constructing proofs. There's plenty of explanation there. There's an introduction. It's good practice when you're writing out proofs, both for the benefit of the reader and the benefit of yourself when you return to look at your notes, is to never just jump into like big long calculations without any remarks. So there's a little introduction here, but before I launch into this multi-line equation, I just introduced what I'm going to do there, just to help the person reading it and to help you when you come back to reading it yourselves. So you should definitely follow that practice when you're constructing your own arguments. And also it's good to finish off with a conclusion statement, even if it is just saying, declaring that you're finished, which is the required property. Just to emphasize to the reader, we're finished. We have proved what we said we're going to prove. Okay. So we should now progress on. So we've dealt with linearity. So the next operation, in kind of natural order of things to consider, would be multiplication. So this is the next theorem, theorem 4.6. So this is called the product rule. It may well be familiar to you already. So this deals with the case where we're considering a product function f, which is the product of two functions g and h. I won't bother writing them out again, but as in 4.5, G and H are assumed to be differentiable at A. Okay, I won't write out the definitions of G prime of A and H prime of A, but again, I've just written them down in the previous proof, so we'll make use of those expressions. Again, just what I'm referring to there is just these two expressions, okay? We have that in our minds at the moment. But I will put in here a warning, and, well, hopefully it doesn't apply to anyone sitting here, but I do see students making this error every year, certain students, and it's a bit of wishful thinking here. Differentiation is not multiplicative. So multiplicative, what's multiplicative? Multiplicative is the corresponding thing to linearity, but this time referring to not the operation of adding different things, but the operation of multiplying things. So in other words, the derivative of f with respect to x, I hesitate to write it down, because I don't want to kind of plant the idea in anyone's mind, so feel free to not take it down. Every year, some unfortunate souls do include things like this in their arguments. They claim that the derivative of f is the derivative of g multiplied by the derivative of h. It's maybe a natural thing to think or to hope might be true, because look, f is g times h, surely then the derivative of f is the derivative of g multiplied by the derivative. Life would be a lot simpler if that were the case, but unfortunately, it's not true. Maybe in very specially arranged circumstances, it might happen to be true, kind of by accident or something, but it is not, certainly not true in general, and is not the way to think, okay? So, if you were ever tempted to think that, don't. Okay, so that's not, of course, there is a relationship between the derivative of f and the derivatives of g and h, but it is as laid out there in the statement of theorem 4.6. Okay, so we need to prove that in our notation, well, in this slightly simpler notation, the derivative of f at a is h of a times the derivative of g plus g of a times the derivative of h. Okay, this is what we're trying to prove. It's a more complicated relationship than that multiplicative one would provide, but it's still fairly nice. It's still a nice property to have. Okay, we can prove this in exactly the same spirit as we proved the previous one. Okay. So we start with the definition. So f prime a is equal to the limit as x approaches a, f of x minus f of a over x minus a. Just the definition of the derivative. But this time, we need to deal not with g plus h, but with g multiplied by h. So when you put in the definition of f, what you see here is we have g of x times h of x minus g of a times h of a all over x minus a. Now again, the g and the h are tangled up together. They're multiplied. What I kind of feel I want to do, see, because we're assuming that g and h are both differential, so these limits exist. These are the assumptions in theorem 4.5, but they're the same assumptions here. So these limits exist. So what I want to do in my manipulation now is to bring out these two quantities. Somehow they're hidden in here. And it looks like it might be possible to do because I've got the ingredients of them. I've got g of x, got g of a, got h of x, got h of a. But of course you have to proceed correctly. You have to tease apart these things in the correct way. And you kind of have one eye on the conclusion you're trying to reach as well. That kind of guides you in the type of manipulation you're going to do. So basically, I want to deal with a quantity like g of x minus g of a. Now be careful, I'm leaving space either side here. I want to deal with a quantity like g of x minus g of a, and similarly h of x minus h of a. Because if I can express this numerator up here in terms of these, then I'll be able to use the fact that the limiting values of these over x minus a exist. So how do you kind of fill the gaps there? Well, by a little bit of trial and error perhaps, or thinking about it, I need h of a here and g of x here. Now, some way that looks a bit, okay, where did that come from? Well, it came from the desire to have some kind of expression here involving g of x minus a, g of x minus g of a, and h of x minus h of a. Okay, because those are the ones whose limits I know exist, or I'm assuming exist. So I wanted some kind of expression, something multiplied by that, or something multiplied by that. So what are these things going to have to be? Well, that's okay. So you certainly get the minus h of a times g of a, so that gives you this term here. You certainly get the g of x times h of x, that gives you this here. Now there's other terms here, but fortunately they cancel out. So what is it? H of a times g of x, and minus h of a times g of x. Okay? So when you multiply out these brackets, you do indeed get back to that exactly. Okay? Next thing to do is to break apart the fraction. Well, we'll break apart the fraction and we'll use linearity to break apart this. Just take, say, the limit of the sum is the sum of the limits. So we've got h of a times g of x minus g of a all over x minus a, plus the limit as x approaches a, g of x times h of x minus h of a over x minus a. So what I've done there is I've taken this large fraction, I've broken apart the fraction at the addition here, and I'm saying the limit of the sum is the sum of the limits, again using linearity. The linearity of the limiting process. I'm nearly there. This thing here is the limit that I want to see. This thing here is the limit that I want to see. So how do I deal with these other factors? Well, in the first case, see this number h of a, that's just some fixed number. A is my fixed point. This limiting process is the limit as x approaches a, as x moves. But a is not moving. A is just some fixed point here. So this is just some real number multiplying this quantity here, which does indeed depend on x. So by the linearity of the limiting process, this h of a can move outside. That's good. There I'm seeing the derivative of g. And something slightly different going on here. Here, okay, here this will turn into the derivative of h if I can take the limit of just this on its own. Yeah, h of x minus h of a over x minus a. But it's multiplied by g of x. Now g of x is changing. But it is going to have a limit. Okay? We're assuming these functions we're assuming g and h are differentiable. So part of that is assuming that they're continuous. So if g of x is at least continuous, then the limit g of x has a limit as x approaches a, and that limit is simply g of a. Okay. So really what we're going to use here is the multiplicative nature of the limiting process. The limiting process is multiplicative. When you take a limit of a product of things, as long as both the things have limits, you can say the limit of the product is the product of the individual limits. So the limit of g of x here is going to be g of a, and that's going to be multiplying the limit as x approaches a, h of x minus h of a over x minus a. So I need a couple of reasons here. Again, I'm using linearity and I think you could say multiplicivity, but it's a bit awkward. Multiplicative property of the limiting process. Okay, I needed the multiplicative property because on the right-hand side here, I said the limit of g of x times that fraction, the limit of g of x, g of a, times the limit of that fraction. And as before, see, I've shown where my derivative of g and the derivative of h, how they are involved in this original expression. Okay? You've got to multiply the derivative of g by h of a, you've got to multiply the derivative of h by g, which is exactly what was required of us. Okay? So continuing onto my next page here, continuing this chain of equations, this is exactly h of a times the derivative of g at a plus g of a times the derivative of h at a, as required. So again, you can kind of emphasize the fact that we've completed the task here, just about by this big chain of equations is just establishing that equation, which is what I needed to prove. Okay. The derivative of f at a at the top does indeed have the required product. It's a really nice argument to see, I think, because it's really putting together like lots of the ingredients that we've built up to now, right, in order to get to this problem. So let's. Are any questions about that? Any clarification? This move, where was it? Here in the middle of rewriting. This move here of passing from this expression to this one. This move, we did a very similar move to this. Look back. Similar arguments in convergence for sequences. Similar arguments for sequences. When we were showing that the limiting process applied to a sequence was multiplicative, well, it's maybe not exactly the same, but it's definitely reminds me of a similar move we have to do. What was that one? Maybe it was, sorry, maybe I'm thinking of the proof. Sorry, no, I think I'm proving continuity, I think. What am I doing? Maybe I'm getting distracted. Scrub that, sorry. It does remind me of something. Maybe it just reminds me of itself. I'm not sure. Okay. Okay, so let's conclude by checking out a few examples of this. So these are in examples 4.3. How are these things actually applied in practice? So if we want to consider a function y here, so which is x squared minus 1, say, by the sine value of x. So this is what we call a compound function, okay? You certainly recognize the ingredients of it, an x squared, a constant minus 1, the sine function, and all those ingredients you can find on the table of derivatives. But on the table of derivatives, you will not find this function, a function of exactly that type. Okay? So we need to use in this case, the product rule. Okay? Well, also in combination with linearity, because you see this here as a product of two functions. You could even call this function here your g of x, and call this your h of x. So the derivative of y at a point A, or point x, whatever, well, by definition, it's going to be h of x times the derivative of g of x plus, sorry, not by definition, but by this property. That's the product rule applied in this situation. So we can just write it out. H of x is sine of x. And the derivative of g, well, if g is x squared minus 1, strictly speaking, we should be quoting the linearity property here. Say the derivative of x squared minus 1, well, that's the derivative of x squared, which is 2x, plus the derivative of minus 1. The derivative of minus 1 is 0. It's just a constant. Then you've got the function g of x unchanged, and that gets multiplied by the derivative of h. So h being sine of x, that has the derivative cosine of x. So there's our answer. Maybe it might be more traditional to put the 2x at the front. I don't know why, but it just kind of looks better. Okay, so that would be the expression there for the derivative of that function y. Second example, you could consider y as a function here, x times the exponential of x times e to the x. Again, that's a product of two functions. The function h, the function x, and the exponential function. So the derivative of y at x is going to be, well, let's say keep the factor x unchanged and multiply it by the derivative of e to the x. Well, the exponential is this special function that it is its own derivative. And then we'll be holding the function e to the x unchanged and multiplying it by the derivative of x. Derivative of x with respect to x is just the constant one. So the second exponential will be multiplied by 1, but we don't normally write that down. Product of 1. So this could be expressed as e to the x into x plus 1. So let's just look ahead at the next properties to come, okay? Which we'll deal with tomorrow, I guess, or at least one of them. So the properties to come are the chain rule and the quotient rule. Now maybe, yeah, in some ways you think maybe we should do the quotient rule after the product rule. Linearity, addition, product rule, multiplication, maybe next comes division. However, actually turns out the way I've organized things, we'll do the chain rule first, which refers to the operation of composition of functions. And we'll actually be able to use that as part of the proof of the quotient. Okay. So the quotient rule doesn't, it can be dealt with fairly easily once we have the chain rule. So the chain rule refers to this very important operation that we do with functions, which is composing functions. Okay, running one function on the result of another. And this really is very fundamental in many areas of math, you know. In some ways, you can say a lot of pure mathematics is about studying the operation and composition of operations. It's very fundamental operation, just doing one thing after another, combining processes. You could express, you know, many different things you can express in terms of combining different processes to make complex processes. So it's a very fundamental type of operation. Okay, here we're considering it as just composing real valued functions. Well, let me just finish by showing you the I think it's better understood perhaps in the other type of notation. So theorem 4.7, chain rule, in the other type of notation. So if y is the composition of two functions f after g, then the derivative of y at a point A is going to be this kind of expression. Now again, it's not as simple as the derivative of f times the derivative of g, but kind of is. This is going to be the derivative of f evaluated at the point g of A, and then that quantity is multiplied by the derivative of g at A. Okay, so y here is the composition function f after g, so applying f to the output of g. And this is how the derivative of such a function relates to the derivatives of the ingredient function. So we'll see the proof of this soon. Maybe tomorrow, or I might postpone it. But proof of this soon, but we'll need using an alternative form of the definition of the derivative. Unfortunately, well, not to my knowledge anyway, we can't prove the chain rule in the similar manner to which we proved the linearity in the product. Just because the nature of this operation of composition is a little bit more involved. So if you attempt a proof of this just following the structure of the other proofs, it's hard to get it out. We need a slightly alternative or a different angle on the definition of the derivative. So that's the next major piece of theory that we're going to see. Okay, I'll finish there for this morning, and I look forward to seeing you all this afternoon. The Options Talk meeting at 1 o'clock.